Good morning, afternoon, people. So we are just starting a bit earlier so that people can have time to join. Right, so another 2 more minutes. Eric, are you seeing my screen with the ACIGS page
Yes,
on? Okay,
yes, I do.
that's good. Yeah. Hmm. I assume you're coming to Joe Asia, isn't it?
Yes, absolutely.
That's great. Yeah,
I look forward to it.
that's good.
I'm coming for 3 weeks, actually.
Hmm. Well,
I've extended with other initiatives.
yeah, Brisbane is always a good place to be in during that period of time where it's winter in the other part of Australia. Brisbane is always the best one to be in.
You have no idea what winter is.
I was in Canada back in 2019 in November. It's winter for me.
Today we had 19 Celsius in Montreal, and that was the warmest day since November, I would say.
All right.
So everybody was out, well, except me, of course. But anyway, okay, I see it's a time. We're on
Yep.
time now.
Yep. Yep. Um, Good morning, afternoon, guys. It's 10 now or 12 in Brisbane, or is it 1 in Melbourne or Sydney, depending on whether you guys have already turned the clock. But yep, we are going to start very, very soon. So I'll just give another minute or so for people to start coming in and join the webinar.
Bonjour.
Hello.
Good afternoon, Jonathan, or evening now.
3 o'clock here.
Okay, still afternoon. Right, so we have Eric and Jonathan joining us as the panelists. So another 1 or 2 more minutes, we'll start off the webinar very, very soon.
Cool. When do abstracts close for 14th ICG?
31st of March
Cool.
is the
All
official
right, good.
deadline.
I have a bit of time. I've got a really interesting topic.
Yes, but you can be quite sure there's going to be an extension. By the way, it's also a call for special sessions and any activity that would be of interest. It's not only for papers.
Okay. Well, we probably need to get together as the TCs then and make sure we have some
Exactly.
sessions. Yeah.
Right, I'll I'll probably start off the webinar.
Okay.
We have a short.
I'm gonna.
Yep. We'll have a short introduction on ACIGS. So while I'm doing the introduction, I think people can still join after, so that they don't miss the main part. So first of all, good morning, afternoon, or evening for Aaron. Yeah. Thank you for joining the 42nd webinar now with ACIGS. Today we have Eric Blond here presenting the title of the webinar. It's Infrastructures Lasting Longer, Using Less Gravel and Emitting Less Carbon. So it's all about geosynthetics and proper management of water. So I'll do a very quick introduction to ACIGS and I won't take too much time. Let's see. Yeah. So as you all probably would have known, IGS has 44 chapters globally. It's probably more now. I'll need to update the slides. And about 4,000 members, including corporate, individual, and student members. We have a dedicated website with acigs.org. And within the website, you'll find a webinar library, which is probably one of the most useful resources that we have online, which has all historical webinars that we have carried out for the last, I think, almost 4 years now. And if you need a certificates for the attendance, so please just email info@acigs.org to request for the certificate of attendance. And just a little bit of marketing for the next conference. GeoAsia is coming up very, very soon in, I think in almost 3 months time, less than 3 months. So we have a very interesting lineup of keynote speakers. So if you're interested to join the next GeoAsia, so please do register as soon as possible. So a very quick introduction to our presenter today. I think Eric probably doesn't need a long introduction. I think most of the people knows Eric Vaughan. So Eric is an independent consultant and registered professional engineer in Quebec and Alberta. He provides technical services to the geosynthetics and building materials industries. So he's also actively involved in several technical committees and associations. He is a chairman of the ASTM D35.10 subcommittees on geomembranes. He is also the chairman of the Canadian Mirror Committee of ISO TC 221. He is also council members, chairman of the IGS TC Committee of Hydro. He probably stepped down from the TCH. And
as well as the TC 221, I'm a vice chair now. But yeah.
Yep, I'll need to update that. And the secretary of the IGS North America chapter. So Eric has authored more than 100 technical papers, conferences for conferences and courses. He's also the lecturer of I have no idea how to pronounce that, but École Polytechnique de Montréal. Yeah. So
that was not so bad.
So welcome, Eric, and I'll pass the presentation to Eric. So if you have any questions, so please post it in the Q&A section. Thank you. So all to you, Eric.
Thank you. Okay. Sorry. I will use the transition for two things. First, remind everybody that it's time to submit proposals for the 13th ICG that will be in Montreal. So the abstract submission is open and will be open until the end of the month. So that's the first thing. Second thing, I believe it's Nowruz today for people from Iran. So happy Nowruz, if I'm correct. I'm pretty sure I'm correct. So it's an important celebration. So I wanted to highlight this. So I did not have any bet on the length of the title. While you were showing the slides of the ICIGS initiative, I see that I've already used once a very long title. So I'm sorry about that. I thought it was provocative and interesting, appealing, because in fact it's highlighting that using geosynthetics should really be something absolutely obvious. Many things which I'm going to present, I hope that at the end you realize that it is obvious, because that's exactly what we should do, and we should not do anything differently than using geosynthetics for these applications. So voilà. Okay, now I need to make sure it works. Okay, that is the thing. So key message I'm going to try to transfer to you, so you know exactly where I'm going. Geosynthetics can ensure durability of geotechnical structures. They can reduce consumption of aggregates while reducing carbon emission. That's really where I want to take you today, with illustration, information, and more details. And where do we start? We start by the fact that we are building infrastructure to deliver function, a road, a bridge, a wall, whatever. And if we don't do proper management of water in these structures, we will see premature degradation of these structures. Very often, engineering is focusing on bearing capacity, on strength. We like numbers, we like kilonewton, kilopascals, but there is the tendency to forget the water. Or sometimes what I've seen, which I think is even worse, is a drainage factor, to have a reduction of a modulus or a reduction of trafficability of something based on the quality of the drainage. This is not correct. Water shall be removed. We shall have zero saturation in a structure to make sure that it's going to perform well. And then we design for it. We cannot play with numbers with water or no water. There must not be any water, period. That's a prerequisite. Like we need to have a foundation to build a structure. We need to have no water in the structure so it can last. It's exactly the same level. What are the effects of water on soils? So just I'm going back to the basics. Negative effects of water on geotechnical structure. So if you have free water, if you have saturation, you're going to have some lubrication of the grains, and therefore you're going to reduce the strength, the shear strength of the material. So the bearing capacity is going to reduce just because it's saturated. In frost-sensitive area, the frost will crack the soil. It will create swelling, etc. So you will actually destroy the structure because of the frost. If you have situations where you have positive pore pressure, you will have even more reduction. So when I mean positive pore pressure, you can have that, for example, with quicksands. If there is more water arriving in the location than the gravity, what can be controlled by the gravity, on the slope on the veneer for a landfill, for example, that's another example where you have positive pore pressure developing at the interface between the soil and the liner, etc. Positive pore pressure will also affect lateral earth pressure, coefficient of lateral earth pressure. So for retaining walls and stuff like that, it's going to affect the soil properties. And finally, when you have seepage in a soil, you will have internal erosion. And internal erosion may lead to the destruction of the structure. At the end, there is an optimum water content. We don't want the soil to be too wet or too dry. So example of a car, we all have cars, I think. So we all understand that. If it's too dry, it's not good. If the soil is too wet, it's not good. If you have an optimum water content, you can enjoy a very smooth ride, no problem. Example of the impact of water on the structure. I took this photo 2 days ago in my hometown. Spoiler, this is my wife and my kid. You can see here that you have a road where the heavier traffic is passing, and the road where the heavy traffic is going is actually almost intact, while on the edge of the road, where you have all the water coming from the snow melting here, we have snow in Montreal, or for whatever was running on the surface of the road, what is accumulating here is creating a true disaster. And that happens to be the bike lane, by the way, so that's always very funny to drive there. So that's an example of how the water can affect the structure of the road. What's happening exactly? We have the runoff. It enters through cracks between the concrete and the asphalt overlay. There is some more cracking. You will have ice lenses developing, and it's a mess. And on the side, we have water entering here. And all this will frost. So controlling the water ingress is as important as the structural design. As I said, water must be stopped from accessing the foundation. So first thing first, we can install a sealing layer on the surface of the asphalt concrete. Or we can install 200 millimeters of asphalt, a very, very thick layer of asphalt, or a geotextile or a waterproofing layer that will seal the asphalt concrete. I mean by geotextile, paving fabrics, impregnated geotextile saturated with bitumen. Other solution to reduce the water ingress into the structure, drainage. So I'm drawing here a red line for waterproofing and a green line for drainage. And here we're having some drainage situation with gravel very often, but sometimes geosynthetics, where we're going to collect the water arriving from the sides to prevent entry into the structure. Another important thing is that we cannot fail in one location. If we have one location on a structure which is degraded, like a pothole, the entire structure is degraded. The serviceability is reduced as a whole by a lot more than just surface. A road with 1% of the surface that exhibits potholes, the road is in bad condition. It's not 99% good condition, it's 100% bad condition because of 1% potholes. Now, if we look at other type of structure, retaining walls. We design the walls, the structural capacity of this wall depends on the horizontal stress that will come from the soil, which is behind the wall, And this stress depends on the properties of the soil with the coefficient of lateral earth pressure. However, if there is no effective drainage, this changes completely. So we can first add the weight of water, and the water may also affect the value of this coefficient. So that's how we get into some situation where the stress is going to be increased by a factor of 2 or 3, up to 2 or 3, and that may actually create some degradation of structures. There is a very good paper by George Kerner, which summarized a research that involved, I don't remember, I think between 200 and 300 situations. And some very important numbers are in there. Up to 2% of the failure of walls are actually failing. There are some level of failings, not a complete failure all the time, but some level of dysfunction of the walls are observed for up to 2%, which is extremely high. It should not be that high. Out of that, 64% of the failures are water related. Water can be many things. It can be plumbing, so a pipe with water circulating that breaks. It can be too much accumulation of water in the backfill. It can be whatever. But it's still 64%. So that's really a good example of how the water can affect the performance, because I'm sure that all these walls were properly designed for reinforcement. It's typically not the reinforcement which is not strong enough. And in fact, in the paper, he indicates that no failure was caused by improper manufacturing of the geosynthetic used in the walls. It's really, really mostly about water and water management. So what do we have? Where do we have water in such structures? We have water which can arrive from the top, from the front wall, and from the back wall, essentially. So how do we do that? We have to install a low permeability layer on top. And on the walls, we can install a drainage behind the blocks, which is typically going to be gravel, and some drainage geosynthetic, geocomposite in the back that will prevent water entry into the region that must be stable. Other type of structure where we can have some water damage, cover soil on top of geomembranes. So when we have a slope, the porous soil, which is especially after construction, where there is no vegetation, is going to accumulate some water. Water will infiltrate into the structure. And if there is no adequate high flow component on top of the geomembrane, water will accumulate there. And eventually we'll have a situation where the saturated region coming from the top of the soil will meet the water table, I would say, in the bottom of on top of the liner. And that will create an entirely saturated region that will be eroded and that can fall down the slope. To prevent that, we must have a drainage. That is something which is well known for such structures. But still, it's one of the typical situations where we need a drainage system. Other example of failure, internal erosion. So there is plenty of situations where internal erosion leads to failure of a structure. This one is a massive, big one, huge one that took place a long time ago. I think it's about 30 years ago. And what happened here is that the compaction of the soil, so the concrete structure was built, and the compaction of the soil near the concrete structure was not possible, but very difficult to do. So some piping started to develop around the structure, increasing the gradient, and that was a progressive erosion that led to the failure that you can see on the right. Now I have a nice video that I'm going to show you of a failure of a canal that was built, so you will see. So you see the water falling. So this canal has been destroyed. Obviously, there was a hole into the geomembrane. And what we see here is that, in fact, the canal was built, on top of a relatively high embankment. And there was no drainage underneath. So what happened? A simple, very small leak in the geomembrane because there is like a couple meters of water. This small leak into the geomembrane was sufficient to create accumulation of water inside the embankment. Then piping started to occur progressively to the bottom of the embankment, and eventually that created the failure that you can see on the right-hand side here. Having installed a drain under the canal to collect and to monitor actually the water seepage through the lining system would have prevented entirely this massive failure as well. So internal erosion of the soil is a problem which must be controlled, but we can also have superficial erosion. So erosion starts usually very slowly. It's some water that takes a little bit of material, and it doesn't seem like to be so important, but it's progressing, accelerating, and eventually you get to a situation where the soil has disappeared. And with the rise of the sea level, with the climate change and the effect on the intensity of rains, those situations where we have superficial erosion will increase a lot. As a parenthesis, in Quebec, we have a situation where floodable regions have been updated, and this has a tremendous effect on the insurance cost. And some regions cannot be insured anymore. The homes cannot be insured anymore. So a lot of people will be in dire situation because of this change in condition, erodibility, flooding, etc. At the end, what's important is that when we design a structure as engineer, what is absolutely critical is to make sure that beyond the adequate sizing is the obvious thing to do. We are engineers, we do size structure, but what we must never forget is to analyze where is the water, where is it coming from, and to make sure that we eliminate entirely any free water in a structure that we want to last, or we control this water at least. We prevent, obviously, excessive pore pressure, and we prevent internal erosion. This will absolutely affect the durability of these structures. And in fact, as I said a bit earlier, the traffic in that case has no impact really on the rate of degradation. What has an impact is the presence of water. It's only the presence of water. I made a quick search and I look on Google search, Google Street View, and I picked in Melbourne. So I thought Melbourne because it's probably more wet than Brisbane. So I wanted to take something in Australia, and it's really random. I just went down on Google to go down onto a road to find that indeed in Australia, it's not only in Quebec with high frost, in Australia as well, you can see that cracking is occurring on the edge. Water accumulation obviously is in that region. I spent about 40 seconds finding this image. I looked for a degraded pavement, and as soon as I had the pavement with some level of degradation, I could immediately see this mechanism where we have the edge of the road, which is more damaged than the middle. So we have geosynthetics. That's fantastic. We're going to be able to use these products to address the water problems that we observe in soils and in structures. The two things that we do that we're going to focus on are filtration and drainage. But before I get there, I want to show you something that I've analyzed on what are the function and the role of geosynthetics in structures. If I look at ISO TC 221, the work group 6 has defined 10 functions for geosynthetics. I put them, it's not random, I put them in a very specific order around this circle to look at how we can coordinate everything. First thing, I put geotextile. How can we distribute geotextiles around this round of functions? So we can see that woven geotextile can do stabilization. I should start here. Geotextile filter can do filtration. Geotextile cushion will do protection, separation, obviously. Woven geotextile can do stabilization. Paving fabrics, so saturated geotextile, bitumen saturated geotextile will do sealing, and we can have stress relaxation product, stress absorbing membrane interlayer. That will also help with the the performance. Now we have drainage products. In blue here, geo-drain, geopipes. We have for sealing geomembrane and GCLs. I could have put them in two different boxes, but it's not really important. For geogrids, we can have geogrids that will do reinforcement and stabilization. Geocells that can do stabilization as well as erosion control. Erosion control mats and blankets can be obviously used for erosion control as well. And we have geofoams for lightweight fills. What I realized is that, in fact, we have three categories of function. One is water management, and it's a big one. Another one is structural integrity of the structure. And the last one is structural contribution. And in fact, if I harmonize the color codes, we can see that in green here, I've put everything which is about preserving the structure, preserving the integrity of the structure, making sure that the structure is not moving, there is not too much rutting, we control the erosion, etc., etc. So it's really about protection. Another one is water management, and water management includes both drainage and sealing, obviously. We are controlling the water. We stop the water and we remove the water. And the last one is the structural contribution. So in fact, we have three categories of products with geosynthetics. And what I'm going to discuss today is really focusing more on water management and somehow on structural integrity, which includes filtration, as I will explain just now. So when we use geotextile for filtration, what we want to do really, it's not about water. It's not about water flow. It's about preserving the integrity of the structure. We want to retain the soil skeleton. So the soil skeleton, which maybe it's important to precise that the soil skeleton is the type of grains within the soil which are used by the stress to be transferred from one side to the other. So that means that what is not the soil skeleton, if it's lost, like we can see here, those two cavities here, it is lost. The particles are not there anymore. They have passed through the geotextile, but the coarser material, the skeleton, is still there, which means a stress can still go from this location to that location, and that means the structure will be preserved, will function properly. The water can flow. We have now a very porous area here, and so the water can pass through no problem, but the soil skeleton is preserved. So with that, filtration is really an integrity function. We are preserving the integrity of the soil structure, and we're letting the water pass through the fabric. When we use geotextile for drainage application, we're going to typically use French drains. So that means we have a geotextile filter, we can see on the right here, which is used in combination with aggregates in that case. So the aggregate is the water transport function, while the geotextile is a filter, which ensures preservation of the integrity of the soil. To work properly, so these drainage structures, in fact, we are using that every day today, but these structures are in fact coming from the 19th century. Modern drainage strategy, which are not based on channels, which are not based on open channels, were in fact developed in the mid-19th century. The concept was developed by Mr. Henry French, who you can read the title of the book here, where he is explaining how to drain land. And what he wanted to do is to control the water table within the area where the crop is being grown. But he didn't want to waste space. He wanted to be able to have some crop growing in that region. Putting a channel here would lose a lot of land. And especially at a time where everything was done with horses and oxes, you don't really want to have so much space wasted. That's more transportation, etc. So he found that putting some tiles and covering the tiles with straw would provide an excellent solution for draining water, for lowering water table in soils, and that was the way to go. So nowadays, we still call these products tiles. It's still called tile drainage in the agriculture industry. But now we are using corrugated polyethylene pipes wrapped in a geotextile filter. And by the way, this used to be done with a shovel. Now it's mechanized equipment which are installing typically 10 kilometers per day. It's very, very high pace of installation. So that's really the origin of modern drainage system, this one. Now let's look at what's happening in dams. I use a dam because it's an interesting application. Dams are probably the most critical application with respect to water management. We want to contain water, so that the purpose of a dam is to contain water. And we want to make sure that the water is not going to destroy the dam. So all the design of dam is based around water management and erosion. And it happens that it's also the first application of a geotextile as a filter. And that was 55 years ago. I was 1 year old when the first geotextile was installed. So this was the Valcroze Dam in France in 1970. So there was two applications for geotextile on this dam. Was one on the upstream face of the dam, where it was used under the riprap, and by the way, I insist, the photo of these slides here were given to me by JP Giroux. They're coming from the Terzaghi lecture, which is extensive and that must be read by anybody that works in filtration. So these photos are coming from this lecture. So that was the first application under the riprap. And the second application was at the downstream drain. So we can see here the limit of the downstream zone of the dam before the embankment was actually built. And you can see here the geotextile which is being installed. So the photo is from 1970. And we can see here also additional finger drains here. This dam is 17 meters high. It's a homogeneous structure. And so it has been in service since 1970. Other interesting application for, so the reason why geotextile was installed here by JP Giroux is because he was not able to find some adequate sand. There was no sand around, so he would normally have used sand because that's what you do normally, for a dam especially, but there was no sand available. That's what led to this innovation and to, in fact, the first use of geotextile as a filter in a large structure. Okay, so now another thing which is interesting for this very large structure in particular. Soils do not have tensile strength, which means if there is some displacement, or like the structure I showed a bit earlier with a massive failure on the dam, you can have cracking appearing in the soil because of the lack of tensile strength. And through cracks of the soil, you can have some piping and erosion developing in these cracks. This would not happen with geotextile filters for the simple reason that geotextile filters can elongate. So it's a very basic properties. We can pull a geotextile and increase its length by typically 50%, up to 50%, 60% for a non-woven geotextile. And that will affect the properties probably, but that will not break it. It can support some level of elongation, which means piping is becoming extremely unlikely when you use a geotextile. Clogging is another problem. Obviously, you need to do adequate design of the filter and installation, but piping through cracks of the soil is becoming extremely unlikely. So combining granular filter with geotextile filters in those structures sounds like the way to go. So voila, geotextile at the end are really ideal materials to prevent internal erosion and to preserve the integrity of geotechnical structures. That's really the part which is important. Preserving integrity of the structure. Now, once we have these geotextile filters, we are doing innovation, or we have been doing innovation 30 years ago, and we have developed geocomposite drains. We are assembling together different products, geotextile filters and a core, and that gives us a product which is sold on a roll and that can be installed and provide both the filtration function and the water transport function. So that's a very interesting aspect. How can we use that in roads, for example? So I presented earlier this situation where a road can degrade because of excess water. So let's stop this water. So we can install, you can see here, we have a geocomposite, which is in that case a very thick non-woven with very coarse fibers. It's a 3 layers product. It's an edge drain, a non-woven edge drain, which is connected to a pipe. And this product will, as you can see here, stop any water from entering the structure. So that's a very effective way to prevent that. And this photo, I took it in 1998. That's my photo on a project I did at that time. With instrumentation and everything. And I looked this afternoon again, I looked on Google Street View. What was the condition of this road after 20 years? So it's interesting to see that with these edge drains, you can see here that there is no degradation. The road after 20 years, obviously there is some cracking because it's winter, it's Canadian winter every year. So there is some contraction of the asphalt, and there is some movement, there is some traffic, etc. There is some cracking. That's normal, but there is no more cracking on the edges. So the road overall behaves relatively well because of the absence of entry of water from the side, because of adequate water management. If any water enters through the asphalt and the concrete here, it's going to fall immediately in the drain. There is no circulation, no accumulation, is going straight into the drain. That's really the best possible location for that. So voila, that's where it is installed. It's not the exact same location. You can see here there is a sidewalk, not here, but it's the same street. And as a reminder, I present you this structure here where there is no such edge drain. I was not involved on construction here, but it is not 20 years. It's less than 20 years, and it is completely degraded. So just to show the interest of these edge drains for preserving water entry into the road. We can stop the ingress of water through asphalt overlays by using paving fabrics and stress-absorbing membrane interlayer. So paving fabrics, it's basically a geotextile saturated with bitumen. And you can add, like you see in the bottom here, a layer of high-strength geotextile that will distribute cracking, in that case, expansion contraction of concrete slabs, and that will distribute this expansion and prevent immediate cracking and immediate deterioration of the structure. Another type of product which is interesting is wicking geotextile. If there is free water in the foundation of a road, in the granular material that is used as a foundation, the hydrophobic nature of the polypropylene that constitutes the geotextile is likely to affect the effectiveness of an edge drain to remove the water from the inside of the foundation, especially given the very small hydraulic gradient. You will have typically anything around 2% as a slope on a road. So if the water has to travel 9 meters in a medium to low permeability gravel to reach a drain on the side with a 2% slope, is going to take forever. So a cracked pavement will be a problem. So using a wicking geotextile will accelerate this transport. And another thing which is interesting is that you don't need to reach 100% saturation near the geotextile. It will remove the water immediately, even as soon as there is enough water near the geotextile. So an example here that I took from one of the papers published to introduce this technology in 2022. So you can see a clear difference between the region where there is a wicking geotextile and the region where there is not. It has effectively removed the water from the top layer. In retaining walls, so similar consideration, the drainage layer will remove excess water from the soil. Here we have much higher gradients. So we're not in the same logic as in roads. We have high gradients, so we will have flow through the polypropylene or whatever material. It's not at all the same problem. The Geocomposite, or the drainage layer in general, will remove the water from the soil. It can act as a protection for the concrete wall. This is especially important if you have frost, because you don't want to have any water on the concrete. Concrete does not like water. That's concrete exposed to water will degrade very fast. So having this drainage blanket near the concrete will protect it and will extend its service life. A very practical thing as well is that it can be installed on a essentially vertical wall. So installing a geocomposite, installing gravel vertically is very hard. It can be done by layer, but it's very hard in general. While installing a geocomposite is easy without any problem. Mechanically stabilized earth walls, similar situation. We usually put the drain in the back for convenience, and also because the drain cannot interact with the geogrid. The geogrid is going through, has to be anchored on the blocks, and therefore you cannot put a drain in that location. So it's still gravel which is used in that location, usually, unless the structure itself offers some drainage capabilities. But voilà. Geocomposite in environmental containment. So they are used for several applications, and they can be used as a primary liner, as a complement to the drainage layer. They are excellent cushion to protect the geomembrane. So it's not only that they're going to deliver some drainage capabilities, they're also going to offer a protection, an effective protection layer to prevent puncture of the geomembrane. It's definitely a combination that works very well together, geomembrane and geocomposite. There are some questions about the service life of these products in environmental applications. However, what is important and what is sometimes omitted is that the service life that you require for a drainage layer in the structure will depend on the application. And I like to use as an example, which is the most extreme example, if you use a geocomposite and on top of a geomembrane as a primary leachate collection layer in the landfill, first thought is that, oh my God, there's going to be biological clogging, it's going to be a disaster, the body is going to be clogged after 3 months. And I will answer, yes, it may be clogged after 3 months, but we don't care a second. We don't care a second. Why? Because the design of the hydraulic layer here is done for the most critical scenario, which is when there is no waste at all in the structure. As soon as you start to accumulate waste, the flow of liquid, if you have a rain, a big rain, the flow of liquid reaching the drainage layer is going to be reduced tremendously because of the absorption in the waste, because of the time, in the delay, the transport of water through the waste, and because of evaporation, runoff, etc. So at the end, what's going to really happen is that as soon as you put some waste, you reduce the need for drainage tremendously. A study was done, I don't remember, in the early 2000s in France that showed that, in fact, once you have a geomembrane cover onto the structure, the leachate generated in the structure will be about 500 times less than what it would be for a rain. And that's considering the most critical scenario immediately after covering, when there is still some activity, etc. So the needs for drainage are highly dependent on where the structure is, where the product is installed. Voilà, so really, again, geocomposite and geocomposite drain and geosynthetics in general for these applications are really the way to go. But now I want to go one step behind again, one step back again, and look, compare why do we need to discuss even that? Because if we think of it, mankind has been managing water for the last 10,000 years. There are evidence of water control structures which are 10,000 years old. In India, there are in the Indus Valley civilization, there are some artifacts of structure which are still working today, which are 4,000 to 5,000 years old. So this is working very well, and we know how to do. And I'm going to focus more specifically on one other example, which is in Italy. the Via Appia. There are still some evidence of not evidence. This road is still used today. It's 2,000 years old. And we knew exactly how to, at the time, we mankind knew exactly how to do this construction. We had a very good understanding of how to manage water, trial and error, whatever. It was not engineering. It was just, we need to remove the water. They were doing what we should be doing today. And this was long before geosynthetics were invented. So I'm not going to pretend geosynthetics are the only solution to control water. It's just one of the solutions. The question is, how much of these materials do we have? How much aggregate do we have? Because in fact, what we have to realize is that aggregates with the adequate quality for construction are among the less renewable resource on Earth. I'm going to give an example that I like, which is near my home, near Montreal. It's a rock. So Montreal is built, it's a rocky area in the middle of the St. Lawrence River, which is in the middle of what used to be the Champlain Sea. It's a clay deposit, and there are a few rocky areas every 20 kilometers, more or less. There is a few of these areas. So you can see this, this hill, which is very nice. Spoiler, there is a quarry in the middle. On this hill, there is a national park. So believe it or not, but the top of the hill is a national park with rare protected species, and we are protecting wildlife here. There is a residential area. It's actually quite wealthy. It's a nice neighborhood. There is another residential area here. There is a ski resort. So the hill is it's maybe 70, 80 meters high. But it gives an opportunity to do some ski. We can drive there and be there in 10 minutes, 20 minutes. And in the middle, there is this quarry. Obviously, there is not much time left. All this is on the same very small footprint. Extraction in this quarry was started less than a century ago. It's probably more like 80 years ago. I don't have the exact number, but it's not very long. And this quarry is at the end of its service life. So when we're done with that, we have to think, are we going to open another quarry here? Are we going to ask people to move? Are we going to cut the ski resort? Are we going to use another of these few mountains we have in the area? There is a limit to what we can do. Okay, I've spoken of Quebec. I'm going to use another example, which is quite the opposite. Dubai. Dubai is a sand desert. It's 650,000 square meters. Dubai is very wealthy because of the oil, and they built this magnificent tower, Burj Khalifa, which is the highest tower in the world. It's 110,000 metric tons of concrete. This is an engineering marvel. One thing which is important and that not everybody knows is that to have a sand with the adequate meeting the specification to build this magnificent tower, the only sand that would meet the specification was in Australia. So they had to transport sand from Australia all the way to Dubai by boat to be able to build this concrete, because none of the sand that is available in Dubai offers the adequate properties. The sand that they have in Dubai is good for anything else, but not this type of concrete construction. So it's important to realize that there is aggregates and there is aggregates which are suitable for construction. And that's two different things. And in fact, it's not something which is new. There are numerous reports, information available on the fact that sand has become a very coveted resource. The quantity of sand with the global increase of wealth in the world, the quantity of sand, the number of construction which are being developed is increasing at an incredible pace. You can see here that between the mid-90s and now, it has almost tripled the quantity of cement and therefore sand, which has been used around the world. We cannot ask these people to stop building. It is the clear tendency. What is the consequence of that? Because the costs are going up, because the need is going up, there are some mafias developing for sand. So again, it's not something that it's not a ChatGPT creation. That is a report which is available online on sand mafia and how they affect the economy. What's happening exactly is that there are some protected areas for wildlife, for natural preservation, whatever. Some people are just going there in some circumstance and illegally remove sand from these locations. So it's illegal exploitation of sand, which creates tremendous side effects. It's not only a question of taxes, it's a question of preserving wildlife, preserving habitat for different species, etc. All the economy is well known, but it's going to continue to happen because that's how things go, and there is a cost involved, etc. So let's go back to our situation. We have sand and gravel. We understand, we know that it's a scarce resource, but we're good engineer, and we're going to say, okay, I'm going to build a structure which is going to last 1,000 years because we are capable to do that. Romans were capable to do it. We're capable to do it as well. And we know exactly how to build with sand and gravel. So it's not really a question of can we do it? Yes, we can do it, no question. But there is a problem. Our needs are changing. This is a Via Appia which was built 2,000 years ago. Practically, yes, a car can go on that road. But this is Rome today. These cars will not go through this road. It is not going to happen. And we have no idea what tomorrow is about. In fact, if we look at it, our needs are constantly evolving, but we don't even know in which direction they're going. We know that the population is growing. That's a fact. We know that the weight of vehicles are growing, so the structure must be thicker, obviously. The speed is changing. In some region is going up, in other region is going down. We have electrification. We want to remove gas car. We want to have electric cars. So we're going to have probably some changes in the technology for transportation. Transportation, we have public transportation. Why not take the bus? Why not take the bike? I bought myself an electric scooter. I love it. I don't use my car in town anymore. Long-term effect of the pandemic. There is anything can happen. Now we work remotely. I work from home. Many people work from home. Nobody is using the roads as before. So some trends are going up, some trends are going down. And that's going to affect how we have to build roads. Long story short, our needs are constantly evolving. It's not necessary to build for 1,000 years because all the infrastructure that we are going to build will be obsolete in a short-term perspective. There is no other solution. Everything is going to be obsolete eventually. However, the quantity of aggregates that we have available remain the same. It will not change. We have a fixed number of aggregates which are qualified for construction that can deliver the properties that we need for construction. Other aspects, practical aspects. Let's say we forget everything about that. I showed you that every quarry eventually will be empty. It's a bit hard to value an empty quarry. Let's say we decide to sacrifice this hill here. We still need to find another one, and this is a dead area. I took a photo, again, Google search. I typed quarry in Brisbane. And all the red dots you can see here, that's the quarries you have in Brisbane. You can do the same exercise everywhere. At the end, there is a limited number of quarries. So what's important to realize is that for each of these quarries, they will serve everything around. So if you have some construction going on here, it will have to come from one of these quarries. Transportation, hauling of all these aggregates will represent a tremendous disturbance. And once they're empty, once all the red dots that you see here are empty, we're going to start to go in the mountains here. And in 100 years, it's going to be further here, etc., etc. It is not sustainable. It is simply not sustainable. The way we're dealing with gravel today is not sustainable. So at the end, in the short term, what will define how we are building infrastructures, it's first performance and cost, obviously, because we are engineers. Any engineering work has to work. and has to be at a good price. That there is no question there. I'm not dreaming. Second aspect, we must have some approach that will favor a sustainable use of aggregates. We must preserve the one we have for future generation. Maybe find a way to recycle them, etc. And the last thing, which is, and not the least, is carbon footprint. I think most people realize that, not everybody, but most people realize that we are on a significant trend to have on climate change. So we need to take care of that, and carbon effective solutions will have to be favored in the near future. Politically, it's not what is a dominant trend right now in North America, but it is a trend that is dominant elsewhere, and it will have to spread around eventually. There is no really other choice. The wildfire that we are observing in North America, the hail event, there was a hail event that cost $5 billion last year. Wildfires in California went to, I think, 48 billion as a cost for insurance companies. So eventually people will wake up. There is something to do. So now next question is, how can we, geosynthetic industry, help reduce the carbon emission arising for construction? I have only 5 minutes left, so I'm going to try to be effective here. Greenhouse gases emission in the construction industry, I've estimated, looking at the report for Canada. Canada has a very good report on carbon emission. We're probably one of the worst, but the report we made is very good. It's hard to pinpoint exactly the emissions for a specific sector because they make sure that nobody is directly identified. So it's always groups. So by regrouping information, I've estimated that it's about 5% of all carbon emissions which correspond to the construction activity. I exclude with construction, I exclude the mining sector because it's a huge component of that. As a comparison, the built environment is about 39% of global emission, and out of that, 28% comes from heating and cooling. So our 5% in construction, I don't want to say we're going to save the world. If we manage to get 10% of that, we're still very far from what it takes, but it is a share that we can deliver, and it happens to be cost effective and to be better for all the other reasons. So it's just a bonus that we have. We're able to contribute positively to that. To do a carbon analysis, we must look at the life cycle of the structure. We must investigate how much carbon was used to build the structure and see how long it's going to last, and that gives us some information on the life of the structure. So in this environment, the typical contribution of geosynthetics will be to save granular material, and we will see that it has an impact on the carbon. To reduce maintenance. By reducing maintenance, we increase serviceability and eventually we increase the service life. So all of that will have an impact eventually on the carbon. So very quick carbon footprint. How do we account that? First, I'm going to use the term A1 to A3, which is for manufacturing, from cradle to gate, in fact. A1, A2, A3. So we see that it's about extraction of the resource, refining of the raw material, transportation to the next plant, production of the resin, extrusion, etc., etc. And we get to the gate. So the gate is the door of the manufacturer, of the geosynthetic manufacturer, but it could be a gravel manufacturer, it can be the concrete manufacturer, etc. And after that, we have A4, which is the transportation from the plant to the site. After that, there are other aspects: installation, consumption during service, demolition. And if we are able to reuse the product at the end, if there is a path, a stream for recycling and reuse of either the product or by a component of the structure, then we get some bonus point. That's how we can have neutral carbon structures or sometimes positive carbon structures. So all this is specific to a production chain, to a manufacturer, etc. We must include all the aspects of the construction. If we look at what's happening with aggregates, because for resin, I think everybody realized that it's oil, which is refined, converted, etc. For aggregates, there is also some carbon. We have to drill, we have to crush, we have to hole the gravel, we have to install, we have to level, we have to compact. All this has a cost. However, surprisingly, or maybe not surprisingly, the gravel industry is not really interested in publishing this information. In the one-click LCA tool, which is a tool that is supported by the IGS to do these carbon calculations, there is one gravel which is presented, which is in Iceland. So that's the one I can show you here. And you can see basically the same as what I just showed you before, the different steps to get to a product that can be used in construction. So carbon calculation, I've used as an example, arbitrary information, 40,000 square meters of structure. And I thought, okay, let's look at, I want to establish an equivalency between geosynthetic and gravel. So I'm going to look, I don't know yet if I'm going to need 100 millimeters, 150, 200, 250, 300, or 500 millimeters of sand or gravel to have an equivalent function as the geosynthetic. So I've made them all. So to produce the gravel, we have a given quantity of carbon which is mobilized. And that's why you have all these layers here. It's depending on the structure. And then to this quantity of carbon which is embedded into the gravel, we need to transport it to the site. And transportation will depend on the mileage and on the quantity, because the thicker the layer of gravel, the more trucks we need to transport it. So you see here for 40,000 square meters, we need 2,106 trucks to be able to deliver 500 millimeters. If it's only 100 millimeters, it's 422 trucks. This is a lot of trucks. I don't want to be the person living next to it and seeing 2,000 trucks driving in front of their home, by the way. So I accumulate these two numbers and I get this graph, which shows how much carbon is embedded into a structure depending on the thickness of the gravel layer. That's for the granular layer. Now I'm going to do the same for geosynthetics. Soon, geosynthetics will have EPD, environmental product declarations, to inform the users on embedded carbon. This is something which is developing. In Europe, they have many. In North America, I've not seen a lot so far. I don't know how it is elsewhere, but it is something which is coming. I use three cases. So as I said, the embedded carbon in geosynthetics depend on the manufacturer, depend on many parameters, the production technique, etc. And you can see that the quantity of carbon can vary dramatically between products. So here it's 0.4 kilogram per kilo. Here it's 1.15 kilograms per kilo, etc., etc. So it's a lot. Transportation also, I've considered that only 50% of the truck was used. That's something you can play with. Here is what I get. Green, yellow, and red are the three different geotextile, and gray is the hauling. So you can see here the transportation of the geotextile represents basically zero. So that's something which is important, because if you compare the carbon, embedded carbon for the structure I'm comparing, one is gravel, different thickness of gravel. The other one is geotextile. Only for transportation, for manufacturing and transportation, we can see that in the worst possible scenario, if we have 100 millimeters of gravel, which is replaced by the worst possible geotextile, after 8 kilometers, after 10 kilometers, well, yes, actually it's 8, we have an equivalent carbon consumption. And we still have these additional benefits that we have with geosynthetics, the tensile strengths, etc., etc. So and that is completely independent of the hauling. We can bring the geotextile from 3,000 kilometers away, from probably even more than that. We can go half around the globe, and it's still going to be less carbon and intensive. So Yeah, if I look, I'm going to skip that because I'm missing time, but in the literature, there are more exhaustive studies which have been done. I have picked one here, which shows basically that accounting for everything, which means not only the product and the transportation, accounting also for installation, considering that in fact, if you put 100 or 300 millimeters, probably it's still one pass of compaction, etc. We still have about 10 to 15% less carbon emitted when we use geotextile for stabilization. Like here, in that case, it's a high-strength geotextile for stabilization. We still have a significant reduction of carbon emission, which is consistent with what I told you before about a few percent, 0.5% saving globally would be what we would get if we manage to be 100% successful on replacing gravel in our structures. All this to realize that, in fact, transportation is really the problem for gravel. That's how we can, if we want to simplify everything, that is a solution. One truck of GeoGrid here is covering 16,000 square meters on the surface. And this truck is equivalent to about 500 trucks of gravel. Obviously, there is less carbon in the geogrids because, as we saw, it's transportation which is going to drive the cost, the carbon costs for gravels. Brief summary. What do we win with when we use geosynthetics compared to aggregates? We reduce the use of aggregates, which are extremely scarce, and we need to preserve them. We lower the carbon footprint. We reduce heavy traffic vehicle, so local residents will love us. We prevent excessive wearing of existing infrastructure for hauling. We reduce construction time. 2,000 trucks is probably longer to put in place than one truck of geosynthetic. We lower construction costs typically, and that would not happen otherwise, actually. And we increase the life of the structure because of all the side benefits which are commonly developed for geosynthetics. One thing which is interesting as well, if we have a separation layer between the clay or the subgrade and the gravel, even if the gravel of the foundation is damaged by compaction, by fracturing, it may still be more usable than if it was contaminated with clay. So there is no question here. We have another benefit that we have not even considered. And we have a better performance and overall improvement of construction quality. But all this is only possible if we have good design and good installation, obviously. And I think, yeah, after that, it's basically the same consideration. And I like this last image because I think that shows that we have already gone a long way in terms of change of philosophy, change of thinking, mentalities. 60 years ago, people would throw oil, used oil in the ground. That's how they would discard the oil after an oil change of a car. Everybody is laughing at that now. But how will people look at us in 60 years from now? We are using gravel and we're throwing it away and we're pouring it in all directions. That's not good. That's simply not good. So I think that we have to realize that we have changed a lot already in our ways of building, and we will continue changing. And we, as a geosynthetic industry, we are really in pole position to take much more space. So that's what I wanted to present. Thank you very much. I'm a few minutes late. I'm sorry.
Thanks a lot, Eric. Yeah, that's okay. I think it's just like 6 minutes late from a schedule. I think let's have one or two questions. I know Jonathan is probably eager to ask some questions. It's very, very interesting. I mean, towards the later part of the presentation, especially on the carbon side. So, yep, Jonathan, if you have any questions.
Yeah, yeah, particularly around the use of geotextile filters in dams, and I've co-authored and will be presenting a paper at GeoAsia on this. But a lot of the guidance on this goes back to our cold Bulletin 55, which was written in 1986, and I'm sure we've learned a lot about geotextile filters since then, and what do we as an industry do to get some of what we know about the materials now and how they can work into the official guidance so that we can use them more.
Oh, I've lost.
We can still hear you.
Oh,
Yep.
okay. I was not hearing anything. I'm sorry. I lost you for a second.
Okay, so yeah, it was around a lot of it, like guidance on dams, like being the I called Bulletin 55,
55?
written in the 80s, which is almost 40 years ago. And what can we as an industry do to get recognition of how geosynthetics can work in structures into bulletins like that?
So I am aware that there is an initiative going on now to revise and publish a new version of this bulletin. It is coming up.
Okay.
I could not tell you when it's coming up, but I know it's in progress. I know that an expert did a first review, I think about 2 years ago. A second expert went on after the first expert and suggested additional change. And with that, I don't know exactly where it stands right now. But it is something which is active, and I don't think it's going to take more than maybe a year before a new version will be published.
Good to know. And the other one was just one of my takeaways from when Jorge Zornberg came to New Zealand and Australia and did a presentation on geosynthetics and roads. And kind of my takeaway from that is if you just add a geotextile between the subgrade and the base, you can double the life of the road. And it just strikes me as crazy that we're not doing that for the cost of not a lot per square meter, but doubling your life.
Yes. I have to say that there is one thing that, because of what you said, there is one thing that I thought we should always change the approach. What usually people who are conservative in their way of designing, they're going to say, oh, if I don't have a filter criteria problem on the base, between my base and my foundation, I don't need a geotextile. That's the typical rationale which is put forward for not putting the geotextile. Acknowledging that they are not completely wrong with that, what I think we should do is change the regulation by turning them around. Instead of asking a geotextile to be installed if the filter criteria is not met, you install the geotextile and you remove it only if you can prove that the filter criteria is met. That's you're opposing you're inverting the requirement, and the natural laziness. It's a bit provocative, but the natural laziness in one hand, or the absence of sufficient data, will make the geotextile the default solution instead of being an option, and that will completely change the quality of the structure. The problem is that the effect of these initiatives will be seen only in 20 years from now.
That's right.
But as an engineer, we are used to think bigger than our life cycle. So I think that's still where we should go.
Awesome.
Yeah. All right. Thanks, Jonathan. Thanks, Eric. I think we probably would wrap up the webinar. So thank you all for joining. We will put up a record shortly on the website. So if you have any friends or colleagues that really wanted to listen to this amazing webinar, so log on to our website. So once again, thank you all for joining, and thank you, Eric, for presenting. See you all.
Cheers all. Bye.
Thank you very much.
Bye.